Recording in progress.
Well, that's loud. All right, everyone, we're getting started. That was just a Zoom call. We're having a recording of this workshop. It's so people, there's like a CS31 midterm prep going on at the same time, which is unfortunate. But for people who are not here recording this, so that was that loud Zoom call noise. Thanks for joining us today. I know it's a Monday, also week 5, so it's pretty hard to get here. Also thanks for coming over here instead of CS76 because we had some pretty big tech issues with the projector there, so we're glad we can use this room instead. But yeah, with that being said, today's topic is going to be linear regression, and it's going to be a pretty cool model that we're going to get into. One of our actual first, heavy-duty machine learning models, which is more like, I guess, a bit more complex than the Canaans we covered 2 weeks ago. But at the same time, it's relatively simpler, and so it'll be great to learn from. Again, the attendance code is up there. It is Turkey if you're on the ACM membership portal. And again, the feedback form, as well as all the links for anything, the slides, the poll later, things like that, will be on that feedback form link tree right here. So please check that out.
Yeah. Oh, also, real quick, we're going to keep this slightly shorter, because it's midterms week, right? And we already started a little late. So it's going to be a little shorter. We're going to still have like maybe an hour of content or 15 minutes. Just a note.
Yeah. Hope that's cool with everyone.
Okay.
All right, cool. So for today, just a quick summary. What we're going to talk about. We're going to go through a motivating example of like, why would you want linear regression when you already have the amazing KNNs? Like, why would you ever want to do something different? We're going to go into like exactly how we do linear regression, which is called through a hypothesis function, which is basically our output model. We're going to go into a little bit of use of math today. We're going to continue that next week, but a little bit of use of math today. And next week, we're going to go over a thing called a loss function, which is really important for machine learning in general, but also for linear regressions. And a funny XKCD about linear regressions, you guys can read. It's like about basically looking at that linear regression in a kind of like skewed sense of like comparing like small time period differences and making that over a long period of time. So yeah, even if you have like no husbands yesterday and one today, that doesn't mean you're going to get one every day kind of. So don't use linear regression in that case, but there are many cool cases that aren't this for linear regression. So the motivating example is midterm based, yay. So the question of the day is, how well will Joe Bruin do on his midterm? As you can see here, he's not really studying right now. He's actually at the game when no one's there, unfortunately, so he's wasting his time. But we still need to figure out, given his habits and what he does, how's he gonna do in the midterm? And so it kind of just gives you a bigger problem of like predicting your midterm performance, right? So we're all college students, we wanna figure out, okay, there's this scary midterm coming up, how are we gonna do in that class? And so remember last week how we broke down the dorm pricing problem of like into features and targets? We're gonna do the same thing this week. So the first question comes is, what might be useful to predict this information? So what type of info will be really helpful to predict midterm performance? Any ideas? Yeah. Say that again. Sorry. Previous averages on the midterm. Yeah. So if in the past, like the previous midterms were like really low scored, then you might not do as well because the test is really hard. Or if you yourself did bad in midterms in the past, you might not do well. Good example. Anyone else? They can be simple, complex, anything. Homework grades, yeah. So yeah, homework grades definitely impact how you're going to do in midterm. So if you got a 0 on the homework, you're probably not going to do well on the midterm. Anything else? Yeah. Time spent studying, yeah. So if you don't study at all, how are you gonna know what to do in the midterm? Exactly. So I hope you all are studying, because I am too. I'll take one more. Could be anything. Come on, it's gonna be at least one more factor that impacts your midterm performance. It can be anything. It can be anything. In the back. Sleep, yeah. I doubt you can do well in a midterm with like 1 hour sleep. Maybe you can if you have a Red Bull or something, but the point still stands that midterm performance is impacted by sleep. So exactly, things like time spent studying, lecture hours attended, all those features you guys all listed are really important to try to figure out exactly what your midterm score might be. And again, these are called features. And so this is information data that we have about the student or the data point we're looking at that might help us determine what their output score would be. On the contrary, on the opposite end of the spectrum, midterm score, kind of flipping this around, is what depends on these features. So like more sleep might mean better score, or less time study might mean a worse grade. On the other side of it, we have the midterm score as a target. So this is a label target, same thing. Basically where this is what we're trying to predict. And this is also what we might have information about before. So like, let's say we had like information about 50 students in the past taking a midterm. Their scores would be the target scores, or like the actual data. And so our goal is basically to figure out the relationship between the features and the target. That's what we're going to get into linear regression. And so what linear regression is going to do is basically it's going to figure out how tightly are these features correlated to the target, and like how do they impact them exactly? Are they negatively correlated? So like, for example, less sleep, or for example, more time playing video games might be a worse score compared to just negatively correlated, compared to like more time studying is positively correlated. More time studying means better grade. And so linear regression will have that encapsulated in its own algorithm. And so with that, we have to figure out how to get our data into like a usable form. And so this is how we represent data, again, it's in a table. And so each row here is exactly one data point in our whole data set. It represents, in our case, one student. So we might have data on like their homework average, study hours, sorry, lecture hours, and then those are all data about them, as well as their target score, which is like their actual percentage score. So that whole row is data about one student. On the flip side, each column is one feature. And so that basically means that one certain category or feature that we're looking for in our data. And so homework average, study hours, and lecture hours are our features in this case. And lastly, in the fourth column, we have midterm percentage, which is our actual target, And so this is what we want to predict. And so our data table is structured in a way so that rows are data points as a whole, columns are features, and the final column is actually our results table. That makes sense to everyone? Awesome. And so with our data in place, with our like ideas of like how we might model this in place, with our features, our target in place, we have to figure out how to model this relationship. And so a way to do that is called a linear model. I'm sure you all have like looked at like linear models, like they're like lines, right? And so like you have the typical y equals mx plus b. But in this case, we have to figure out what m and b are, which is what we're going to use machine learning for. And so I can't spoil this, but what are the parameters of a line? This is a pretty easy question, I think. But just shout it out if you know the answers. There's two of them, by the way. Slope and point. That can work, yeah. So you can use slope in a point slope form, yes, and that does work. There's also an alternate form that we're going to use more prevalently for lines in this class or in this workshop. Yes, exactly. So we're going to use slope and y-intercept, or in this case, as the machine learning people call it, like slope and bias, or weight and bias in this case.
Okay. Yeah. So what we want to do is now predict the score given some features, right? And what ML is going to help us do is find that. Oh, let's change the picture actually. Yeah. What ML is going to help us do is find the slope parameter and the bias parameter. Now, if we abstract this for a second, let's forget that we're dealing with a line. What we're really doing is finding some kind of a pattern. It's a very generic way of thinking of it, but a line is essentially some pattern that relates data. And at a very high level, that's what ML is helping us do. It's finding this overarching pattern, right? And in this case, with the line, the pattern is completely determined by what the parameters of our model are, which is the slope and the bias. Slope and bias. So yeah, so like Nikhil was mentioning, In ML, we call the y-intercept a bias. And because the reason we do that, right, is because in higher dimensions, we don't actually have a line. It's this plane in 3 dimensions. It's the hyperplane in n dimensions. So we don't really call it an intercept. It's just a bias. It's a generic term for that intersection point. Okay. So again, at a high level, right? The way ML is going to help, see the picture. The way ML is going to help us, right, is that we have the data, which is that table we looked at earlier, and we also have the results, which are the midterm scores. What our ML model is going to do is find the pattern that relates these two things. That's again the high level picture. ML outputs this pattern. Okay. Yeah. Any questions about that? Okay, we're good. Great. So let's formalize what we've learned. Right? First thing we're going to do, we're going to define something called a hypothesis. Now, I think everyone knows what a hypothesis means in a general sense. It's a guess, right? It's like saying, this is what I think something looks like. So we're going to call that y hat. That's our hypothesis. And essentially, it boils down to becoming a function that will output the score given our features as an input. So let me repeat that. Y hat is the hypothesis. It is our guess. It is our model. It is a function, right? And it's what's going to output our predictions. And this is actually what we want to find. If we have this, our problem is done, right? That is our objective. We want to find this y hat. Our input features, we're going to denote them by x1 through xn. And these are the values that plug into y. So we have y hat of these values, as they'd say. What are these input features? It's the stuff we discussed before. Hours spent studying, number of lecture hours attended, sleep, right? Those are represented by x1 through xn. And our goal is to determine y hat. So mathematically, in nice clean LaTeX, that's what it looks like. We have a function y hat, which takes in x1 through xn. This is just notation, but it is important notation as well. We're going to use this throughout the rest of the presentation. So any questions about this? Okay. How do we use this? So suppose we have our input features. If we want to use a linear model, okay, just animation work, I guess. So the way we're going to break down this y hat in a linear model is essentially to generalize the line formula. So how do I do this here? Okay. So let's suppose we look at only the first two terms right here. Y hat of x is equal to b plus w1 x1. Let's forget about all this other stuff, right? If we just look at this, we have the equation of a straight line in 2 dimensions, right? What do we have? We have 2 parameters, we have the bias, and we have some weight. x1 is just representing our x-axis. But now, we don't have just a single feature. We could have 100 features. We could have 10 million features. What we want to do is have a weight for each of the features. So each of them has this W1, W2, Wn associated with it, right? It's a generalization of the linear model. So I was talking about before, it represents this kind of plane or a hyperplane. But the formula is super simple, the name is super cool, but it's a really simple formula. And the way you think of this intuitively, each of the weights determines how much a feature matters, right? If this weight was 0, it means this feature doesn't matter at all. If this weight is 10 million, it means this feature matters a lot. That's the intuitive way of thinking of it, right? And yeah, one more note, these weights can be negative. What does that mean? It's like saying the amount of time you spend playing video games is going to negatively affect my midterm score, right? So if x2 was the number of hours spent playing video games, w2 was the weight, w2 would probably end up being negative, okay? That's kind of this is an important slide. So does anyone have any questions about this? Oh, yeah. Oh, sorry, once more? The role of the bias? Oh yeah, sure. So the bias, essentially what it can do, this would be good to draw, but okay, let's think of this way. Suppose we didn't have a bias term, right? What we have is a line passing through the origin. And that is something that will always happen. What the bias allows us to do is shift it up and down. So it gives us that extra flexibility. Does that help? Cool. Any other questions? Okay, I think we are good. Let's see. Okay, so let's talk about the weights. Let me move this aside. So the weights of our model are what we call the parameters, and these are these W1 to W1 to Wn and B, right? And this is what we want to learn. So let's step back, right? Our model is completely determined by the weights and the bias. If we have the weights and the bias, we have our model. If we have our model, we have our answer. So if we have our weights and our biases, we have our answer, right? And the way we change the output of our function is by changing these values of B and W1 and W, okay? So the purpose of machine learning is to find the best possible values of these weights. What best is, we'll define in a second, but we want to find an optimal value for these weights to kind of make the predictions as best as possible. Okay. Model, great. So this is where the scary looking math comes in. So we have our original formulation of the model, y hat x equals b plus w1 through wn. The way we can represent this in matrix notation or vector notation, as you prefer, is like this. We can represent the features as this row vector and the weights as this column vector and multiply them. Maybe a more intuitive way is just take the dot product. We have one vector of size n, another vector of size n, take the dot product. That's what you get up there, right? It's just w1, x1, w2, x2. This is a really clean, simple notation. As you can see over here, it is just x dot w plus b. This is helpful right now because, sorry, let me put it this way. This may look simple right now, but when you get in neural networks, we're going to use the exact same kind of structure and the formula still works. So it's a good way to start thinking about this right now itself. Okay. Any questions about any of this? Okay, we're good. Right. Okay, that's good. So just to formalize kind of the parameters once more. Input x, n dimensions. If our dimension is n for the input vector, our dimension must be n for the weight vector. Those two must kind of one-to-one correspond, right? Each input feature must have an associated weight. The bias b in this case is just a real number. It's one single value, like 3, for example, right? That's all we need for the bias. And again, the way it works, I can't stress this formula enough because it forms the basis of all machine learning, right? Is that we kind of weigh each of our input features with this weight matrix. It kind of uniquely determines this model, and this is what makes these weights so crucial, right? And we don't need to focus on this formulation because it kind of really determines everything. Okay. Okay, once again, any other questions? We have an activity next. Any other questions? Okay, cool. So let's look at our polling activity. What we're going to try and simulate in a very, very approximate sense is we want to know which feature impacts your midterm scores the most. We're going to literally take a poll, right, of all this, and we're going to figure out what is the factor that determines the midterm score the most. Using this, we're going to create some sort of a linear model. This is not the way machine learning does it, of course, but it's going to give you a sense of how this thing would work. So I'm going to give you a QR code, as always. Let's try this out. And I'm going to start writing on this code. Cross function. How long we put it?
Not too long. Oh, we can send the last function. Yeah,
Oh, okay, we've done the 45. Right.
All right.
Has anyone got the link? Any troubles with the link? What's up? What's up? Oh yeah, you guys need to vote. Is it not? Let's do this. Maybe I should get another tab. I don't know. Is this not what you see? What? That's very funny. Okay, I'm gonna just literally make a tiny URL for this. Oh, come on. Huh. Sorry about that. Let me track W3. Okay, yeah, just use this URL. And for those who didn't see, yeah. Thanks for letting me know. I did not know that would work. Does that work better? Everyone access the poll? Yeah, that's good. That's good.
Can you guys vote on
Can you guys vote? Come on. All right. All right. All right. I got an idea. Share participation. Copy link. We track W342. Let's really hope this one works. This is one we had before, no?
Yeah, you have to start the poll or something.
Oh, maybe you're right. Or maybe I fucked up that. Okay.
Should we do like a, I think I raise your hand then for that.
We could.
I think we can get it done soon.
Okay. Does the poll, does that old thing work now? My bad, my bad. Okay. No? Wait, I see votes.
Which link did you use?
Which link did you use?
Good.
Okay.
But how'd you fix it? Just wondering for anyone else. That's cool. Works. All right, cool. Number of ads. Yeah.
Nice, that's cool.
Dang, no one's about number of hours of sleep. Huh?
Damn, the grind is real. Okay. It's a good note. Present mode.
One vote.
Yeah. Okay. Come on, guys. Midterm season. Let's channel it.
Wow, I'm actually super
Ooh,
surprised.
this is a tough competition. Anyone else want to get any final votes in? Give it 10 more seconds. Every vote counts. All right, it's gonna be good. So what I want to show is, how do I exit this? Come on. All right, beautiful.
That was close.
Yep. So I want to show this, right? Let's do this. So where did our pool go? It was not that. All right, there we go. Perfect. Great. So I want to think about what our model could look like over here, right? I'm going to say that y hat, I'm going to take in how many parameters do we have? Which are our parameters and how many do we have? 5? Okay, I see a bunch of 5s. Good. So we're going to take in x1 through x5. And how many weights should we have? What's that? How many weights? Okay, hands up. Good. 5 weights, right? Now here's a very, let's say, a silly model, right? All of you have decided that study time is the most important. So I'm going to assign study time to be my most important weight, right? So I'm going to make it 14 times x1. Similarly, exam time is super important. I'm going to make it 14 times x2. Similarly, now let's look at this. Number of other classes has 0. So all of you guys say our data is saying that number of other classes does not matter. So I'm just going to make it 0 times x3, right? Similarly, 2 times x4 plus 1 times x5. Okay. So this is okay. Firstly, this is a very intuitive example. It's not how machine learning actually works, but this is a really good visualization, right? It shows us that the weight is associated with importance. Let's say we had another weight, right? Let's say we had another parameter called, I don't know, number of hours spent playing video games, right? That's x6, video game time, right? I'd imagine, let's say that's a super important factor. It's like it has a value of 8, but it would have a value of 8 in the negative direction. That's not showing through our poll, obviously, but it would have a negative value. So what I'd do, I'd say it's x8 times x6, right? So the weights, again, they represent importance in this case. But now let's make a note of one more thing. Exam difficulty. An increase in exam difficulty should decrease our midterm score. So in this case, we'll make this negative 14. Okay? Does this make sense to everyone at a high level? Okay, sounds good. So I'm gonna go back to our presentation and let's talk math. All right.
Awesome. So now that we have that understanding intuitively of what linear regression is, let's go into a little bit of the math today, and then we'll go into it more next week, but a little bit of it today. And so the first part is derivatives. I'm sure all of you are either in a calc class or have taken one. So we'll go over this a little bit quickly. But basically, a derivative is the rate of change of a function. So basically, how fast is the function increasing or decreasing? And so if it's positive, it's increasing. So as over here, the function is increasing, so the derivative is positive. On the opposite hand of this, opposite side of this, if the derivative is negative, where a function is decreasing. Has everyone taken or done derivatives before?
Show of hands. Yes.
Derivatives.
Okay. Looks
Derivatives.
okay.
Okay, cool. I'm gonna skip past this because it's like, yeah, I don't want to repeat stuff that you've already learned. Partial derivatives, I'm assuming not everyone's taking multi, so I'm gonna go a bit slower over this, but it's gonna be pretty similar. So a partial derivative is basically over multiple dimensions, and so let's say you have a function of more than one variable. So now you have f of x, y, but that takes an x and y, so that's 2 variables. And so you might wonder, how do you take a derivative if you have 2 things that are changing? And so the way you do that actually is that you have 2 partial derivatives for a function that takes in 2 inputs. And so in this case, for f of x, y, you have a partial with respect to x and one with respect to y. And so for example, to get the respect to x partial derivative, which is called the partial derivative with respect to x, we assume y to be constant, so like a normal number, and then we take the derivative normally. And so example here, let me move this a little bit out of the way. Oh, I'll move it like here. So we have an example f of x, y for you, which is 2x plus 3y squared. And so for the first partial derivative with respect to x, we're going to take y as constant. And so now we take the derivative with respect to x. So what's the derivative of 2x? That's 2. Just apply power rule, straightforward. And what's the derivative of 3y squared with respect to x? Well, y is constant with respect to x. And so we're going to say the derivative of a constant is 0. So our whole partial derivative is 2. And similarly for partial with respect to y, we have 2x is constant for y. And so we're going to ignore that basically and say the derivative of 2x is 0 with respect to y. And so now we have 3y squared, and the derivative of 3y squared is 6y. Any questions about partials?
Who here has seen partials before? Not sure.
All right. Cool.
Okay. Let's do one more example first.
Yeah.
Okay. Let's both?
Yeah.
Okay. Let's do one more example. This, and I'm gonna. Can we expand this enough?
It's fine. Just do that for people here.
Okay, bet. All right. So let's do another example, right? So let's say we have f of x comma y. Can anyone see this? Yes? No?
Visible.
Back in the back? You can see it? Oh, great. Okay, perfect. Right. And what is our previous example? 2x plus 3y squared. All right. Let's do something more interesting. Let's say x cubed plus 5x plus x squared y. All right. Something like this. Whole mess, right? So we have two variables. That means we have two derivatives. Plain and simple, right? So the first derivative, we use this fancy delta, right? We don't have the d, we use a delta, just for kicks, right? What we're going to do, let's consider all the y terms to be some constant, right? This y, for now, you have a pen? No, we don't. Oh, unfortunate. This is just some constant, right? I'm going to say const. What do we do with constants? We ignore them. We don't care about them. They are just, it might as well be the number 2 for all we care. X, on the other hand, is our variable. Let's take the derivative of this, 3x squared, right? Derivative of this, 5. This is the tricky one. Y is a constant. For a second, let's say this was the number 2. What would the derivative of this be? It will literally be 2x times 2. Let's get rid of this, put back y, and put back 1. That's our partial derivative, right? Y is a constant in this case. So I'm going to go over the partial of y now. Can anyone tell me what the derivative of this term is with respect to y? Shout it out. Yes, very good. 0. This term. Very good. This term. What's that? Once more? X squared, exactly. This is a tricky one, right? Let's do the same trick we did before. X is a constant. I'm going to call it the number 2. Literally, I'm just making this up. I'm going to call it the number 2, right? Derivative of this term would just be 2. So in this case, I'm going to get rid of this now, put back x squared, get rid of this, put back x squared. So those are our two partial derivatives. Does that sort of make sense, everyone? Was that helpful? Awesome. All right.
Awesome. So now we know partial derivatives. Let's go. All right. So yeah. So in general, that was a two-input function. it also works with n-dimensional functions. So if you have n inputs, x1 through xn, the same kind of idea applies. Where basically, if you're taking the partial with respect to one xi, you hold all the other x's to be constant, and then do the same thing with derivatives. And so it's very like it's inductive in that way. It keeps going for any n that you have. All right, and so with that, we're going to do an example with like a bigger dimensional gradient. And so this is like an n-dimensional one. And so a gradient is actually something we're going to talk about really briefly. It's actually really important. It's actually probably one of the most important parts of machine learning is involving gradients. And a gradient is basically the collection or like a vector made of all the partial derivatives of a first function. So for example, for a function over here of two variables, the gradient would be combining df dx and df dy in a vector. For n dimensions, it'll be df dx1 all the way to df dxn, if that makes sense. So the gradient is basically a vector combining all the different partial derivatives for each input. Does that make sense, everyone? Any questions about that? Actually, I'll say that. We'll go through an example just to make sure it's clear. But yeah, it's really important to understand gradients because gradients are not too complicated, but also really important to understand. And so I'll move this out of the way. Oh, man, Zoom time. All right, cool. And so a quick example here is, so we have a three-dimensional function called, which is f of x comma y comma z. That's x times sine y plus 2z cubed. Pretty like typical, or not typical, pretty usual three-dimensional function. And so our gradient is going to be a vector that contains the f dx, the f dy, and the f dz, the three partial derivatives. And so what we would do is like as Sedan did it over here, calculate each partial derivative with respect to that variable, and then put them all into a vector form, and that's the gradient. So in this case, if you want to try it out yourself, just in your free time, taking the gradient of this function would be taking the partials with respect to x, y, and z. And so taking it with respect to x would get rid of that x in the first term, you get sine y, and it's similarly for the other two. And so the important thing to think about here is that the gradient is just basically combining all of the partial derivatives. All right. And so to review that real quick, I'll just have anyone who has the answer shout it out. But taking the gradient of a pretty simple function called x squared, y squared, z squared. Just hands. Just two hands. Yeah. If you have the answer to the gradient, just raise your hand. I'll call on you.
Oh, I said let's do hands for voting.
Oh, hands for voting. Okay, that's a good idea. Okay. Yeah. Okay. What was it? Okay. Take a minute, think about it, and we'll do hands for voting in a second. Yeah, that's a bad idea. Also, they're making this loss function that's a little bit more like meaty content that just for like these people who are like this. Okay, we'll do that. And we'll do that. Just like I'll pick the section. All right, let's go through it real quick. Hopefully you got some time to think about it. Who thinks it's answer C? C, 1/3 x cubed, y cubed, z cubed. Any takers? All right, I see you're all smart here. That's awesome. Yeah. Let's go with B, 2x plus 2y plus 2z.
Looks pretty good to me. It's pretty good. No? You sure? Okay.
Wow. Okay.
Okay.
All right. Let's go with answer A, 2x, 2y, 2z.
All right. Very good.
And answer D, anyone? X squared, y squared, z squared. Awesome. Nice job, guys. So yeah, it just you take the partial with respect to each term. So it's pretty straightforward. Each of them is 2 times the variable, so 2x, 2y, 2z, and you put it in a vector. That's what you get. That's a gradient. Any questions about gradients in general, or taking them or calculating them? Awesome. All right, so before we go into a bit of code stuff for today, we're gonna talk about one really important concept in machine learning in general, but also one feature that makes our linear regression different from our KNN is the loss function. And so it sounds really negative, like a loss function. What is this? Like, why is it so sad? And so it's important though, because we need to figure out how can we get our model to be better. And so at the start, right, our model's kind of random. We're just taking in a bunch of features and saying, we think it might be like this score output as a result. So like we might take in like all those data points about like number of hours studied, number of games played, number of like exam difficulty, right? But like at first, our model's not gonna know anything about the data space, right? It's not gonna know how to weight them. And so we need to make our model improve and like make those weights better and fine tuned. So our loss function is how we're gonna end up making our model better. And so the loss function measures the error in our predictions for our data points compared to the target values. So basically what we're going to do is we're going to pass in from our training data set, our data, we're going to pass in those features. We're going to run our model on those features. So we're going to run like y hat equals w1, x1, w2, x2, all the way to w and x and xn plus b. We're going to get that score, but that's a predicted value. And we're going to compare it to the actual true target value. And our loss function is going to tell us how bad a prediction was. So a really high loss is going to be like, yo, your model stinks. You need to make it a lot better. While a low loss is going to be like, wow, this is a really good model. You're pretty accurate. And so our goal is to minimize our loss function. And so an example of a loss function is called mean squared error. You all probably heard of it. It's up here right now. And so it takes in basically the hats on top of it are basically our predictions for a bunch of data points. And so let's say we had m data points in our data set, right? And so our loss function is going to take in our m predictions from our model on those data points. And what it's going to do is basically for each of these data points, we're going to start here. Okay, so we're going to figure out, we're going to compare our prediction to the actual value. So we're going to say like, okay, our actual value is 86. Our prediction was 95, right? Subtract those two, we're off by 9, right? Or negative 9. But we run into the issue if we use the subtraction of what if our score is negative, what if our difference is positive, right? So let's say we had a difference of -9 once and a difference of +9 the other time. If we just didn't square this, we would have had canceling out errors. So I guess a good way to think about it is actually on a whiteboard actually. So let's say, simple table right here. We had, okay, let's do, hopefully you guys can see this. I'll read it out anyways. You guys see this or no? Everyone see this? Yes? Okay, I'll say it out too. So let's say we had a couple scores, 86, 95, 77, 63, let's see, 100 and 90. So in this case, let's calculate the difference between all these terms. Like let's calculate y minus y hat. And so this case it'd be 9. This case it'd be -14. In this case it'd be -5. And so our sum is actually going to be -10. And so you might think -10 out of 3 approaches, right? So that's like -10. Our average error would be like -3.3, right? And so you might think that's not that bad, right? But look at the magnitude of these errors; they're actually pretty far off, right? And so the reason why we square these numbers here is to get rid of this negative problem. So as you see here, the 9 and 14 are both pretty off, but because they're opposite signs, they're like canceling each other out in our end sum error. And so the way we get rid of that is that we square all of our errors. So we get, in this case, 81 is 9 squared, 196, I believe, is 14 squared, and 25 is 5 squared. So you add those two together, you get a big number, and divide by 3, you're like, oh my God, my error is so super big, and my model is not good, right? And so as a result, you can basically see a better visualization of your error is by squaring the differences. that make sense, everyone? Why we're squaring stuff? Awesome. Apologies. And so we're taking our difference between our predictions and our true values. We're squaring them to get rid of that cancellation problem. And we're doing that for all our m data points. So we have 3 here. We have m in theory. And so we're going to take the sum of all of those. And that's our total sum, which is like, here it's like a big number. And so we're going to average that out by number of data points. So basically, we're going to figure out, on average, how bad is the squared error, which is why it's called mean squared error. Any questions on mean squared error? Awesome. Again, it's not the only loss function, but we will be starting with this one because it's not too complicated, but also really useful and used a lot in industry as well. And a couple of notes, like as I said, yeah, y hats are our predictions, y are our actual true values, and I is like the sample number. And so before we had our loss function in terms of our predictions, right? In the last slide, we had like, let's go back to that real quick. We had L was in terms of all of these predictions up here, like y hat 1, y hat 2, y hat m. But remember that we actually know how to calculate our predictions. They're actually dependent on our weights and biases. They're actually W1, X1, W2, X2 plus B, basically, right? And so we can think of our loss function as a function between our weights and our bias instead. And this is a really important way to make our loss function really useful for making our model. And so as a result, you can kind of see how like we actually have a formula for all of like the y hats in our input to L. And so we actually could like substitute in those inputs up there. And so our loss function is not actually a function of our predictions. It's actually a function of our weights and biases because those can calculate our predictions. Does that substitution make sense to everyone? So just like a plug and chug into our things. Any questions about that? That's like I said.
Let's do this.
Yeah. All right, cool. And so in order to actually learn our weights or get better weights, our goal is to minimize loss, right? We want our model to tell us that we want to make our model as have as little error as possible. And so our goal is to minimize that. And so we know our loss function is actually a function of our weights and biases now. And so with that, we can actually change our loss function in theory. We can make our loss alpha better by updating our weights and biases. So that's our goal with machine learning in general, is to basically update our weights and biases because they determine our loss function, right, and how our loss outputs. And so if we update these weights and biases, we can actually make our loss go down, and that basically signifies a better model in the long run. And so a smaller output loss is a better model, and on the flip side, bigger output loss is a bad model. And we need to find ways basically that our loss is as small as possible for all our data points. So like you could say, like looking at our data over here, what if we always predict 95? It's perfect for this data point, but we want it to be good for every data point. So we're running weights in general to minimize loss overall. So you often can't get zero loss, but you can get really close to zero loss in general. And so
These right? Thank you so much.
So we're gonna figure out how we do that next time. Kind of like a bit of a cliffhanger, but we don't want to go over too much detail before everyone else comes back. Also midterm season, but in exchange, we're gonna go kind of more in depth into a really cool code example with linear regression. So we'll get into that right now.
Okay. Let's go to the code.
Yeah.
Okay. You can take it, but
yeah. Can we go to slider?
Which slide is it? Yeah, so as a teaser, this is the cool visualization that you'll understand next time.
Yes.
Really cool, Jeff, but let's go to implementing. Yeah, this one. Yeah.
All right.
So it's slide 38, 39, everyone.
So you can follow along at tinyurl.com/btracks-f21-vw3/demo. We'll be going into a bit more depth in the code today because we have a bit more time. But yeah, feel free to go on there. All right. Let me reset it. Yeah, but how do I reset again?
You know, 3 outputs.
Actually, that's fine.
Yeah, that's fine.
All right. Is this big enough for everyone? Can I increase this font?
I got you. Let's see. Edit.
That's fine. That's fine.
Clear outputs. You want to do it?
That's fine. Yeah. All right. Can everyone read this? Yes, we can make it bigger. Yeah. Good, bad, bigger, small.
In the back.
Good. Everyone else in the back? Good. Cool. All right. So similar to last week, this is going to be a mostly a library approach to doing things because, again, by the end of this course, you all should be implementing this yourselves. So we're not going to actually go into like making it by scratch, but there are some really cool libraries out there, which we talked about last time, which we'll go into that actually help us make this really a quick process. And so first off, again, we're going to go with Numpy, import Numpy. And so Numpy, as Sudhanshu mentioned last week, is the basically scientific computing library for Python. It's like basically anything numbers, like arrays, things like that. So it's really helpful for machine learning because machine learning is a lot about vectors, matrices. So Numpy is like a staple in a lot of machine learning programs. Next, you have a library called Scikit-Learn, also abbreviated as sklearn and like imports. And so that library is going to be more about models, data sets, things of that nature. And so this is we're going to get our data set from here, as well as linear regression, a cool method called train test split, which is pretty important for getting your data set like more processed for input and output. 2 metrics, mean squared error as well as R2 score, to figure out how bad your model is doing at the end, as well as the plotting library, matplotlib. These are all pretty common in like machine learning algorithms and machine learning applications. So we'll get into more detail in later weeks about how to use them. But for now, just we'll explain what we're using when we go through them. For now, just import, yeah, run anyways. I promise you, we're not trying to hack your computers with this. So yeah, don't worry.
Real quick, could everyone run this because you can make a copy otherwise?
Yeah, sorry for mentioning. Yeah, if you can't run this, go to. Actually, you probably won't be able to run this. So go to File, save a copy in Drive, to make a copy in your own Drive. Or if you don't want to use it later, open in playground mode also works. Yeah. Cool. Cool. So with that, we're going to make some data to actually we're going to regress on some data that we're going to make. And so what we're going to do is we're going to have 300 data points. We're going to space them on the x-axis evenly about from 0 to 50. So this is what this does. So we're going to get 50 data points on the x-axis, evenly spread, or 300 data points on the x-axis spread out between 0 and 50. We're going to calculate some noise. So we don't want a straight line, right? Because a straight line is really boring to model. So we're going to add some noise to our data points. So this is why we're going to add some multiplier times some random numbers to our output. And then we're going to create some y outputs for multiplying the x's by 4, adding 14 and noise. So it's kind of random numbers, I agree. But the goal here is that in theory, if the noise is not too bad, our regressor should fit to y equals 4x plus 14. Is the idea here. So we created 300 data points based on x. We created some noise and created some y's based on a line as well as some noise. And so our goal is to basically have our model fit to 4x plus 14. Any questions about that?
So just to make a point here, right? In real world, obviously we wouldn't have this 4x plus 14 formula. This is something we are generating data. That was really funny. All right, bet. All right. I think we've run out of time, unfortunately. 8 o'clock, I think it closes, but that's fine. So I guess everyone has the code up, right? Somehow. let's walk through this.
Okay.
And wrap it up.
You have a Zoom link?
I do have a Zoom link, but
Sorry about that again. Yeah, it's just like we have that room, but they didn't. I don't know why they didn't tell us that we don't have the projector. So we'll have to get that figured out for next time. But
how do I copy invitation? Oh yeah, for sure.
It'd make it easier.
Copy invite link. F21. All right, it's F21 B-track Zoom. Oh, all hyphen. Oh, it's a password. Oh, come on. Okay, isn't it? Yeah, if there's a password, it's 724195.
So the link is tinyurl/f21b-3track-zoom. The password is up there, 721.
Oh, it's 721. You don't need it? Oh, beautiful.
Okay. Yeah, again, sorry about the projectors, but I guess Zoom we'll have to be back on Zoom in person, which is yeah. Vietnam War flashbacks with Zoom, I guess. Yeah.
Let's
Is it here?
yeah.
Here, right?
You guys can see the our screen, right? Okay, beautiful.
All right, cool.
Let's make sure. All right, great.
Cool. All right, so we got to the making of data. We're going to do that using a function called train test split. You went over it a little bit last time. We'll go over it again today. And basically, so we have our data points and our Y data points, right? There's 300 of them. We're going to split them into a training data set and a testing data set. So that means that we're going to have a certain section of that data set that we can be perform all the learn off of. And that's the training data set. We're going to learn off of that. And then the test data is going to be there. We're going to have that kind of hospice in the corner. And then once you train our model, we're going to be like, yo, you're free. Like our model will try that and see how it does with like outside data, basically. And so the goal of having testing and training data separate is that you don't want to see how accurate you are on data you trained on. You already have to learn from it. So you want to see how you do on data that you don't know anything about. If that makes sense. And so what we're doing here, we're passing in our X data points or Y data points. We're saying that we want 20% of our data to be in our test data set, and we're shuffling the data, which is nice. And these two commands, I won't go into much detail about, but they're changing the shape of the array, which was not good. And now you can see how our data looks like now. And so as you can see, our data, our testing data is split. It's mostly testing data, it should mostly be blue, but there are some interchange red points around there. And so we're going to take the blue red points and test on the red points. It's the main thing.
So real quick, right? Let's make sure we understand what's right is like our initial data was generated using y is equal to 4x to 14, right? If you didn't have this noise, you have all the points kind of on one line. The noise kind of shifting around, right? Making it all more distinct. Yeah.
Exactly. Yeah. So now it's interesting, right? Because you can still see the general line structure, but it's not quite a line. It's like, yeah, you can't make one line out of all these random data points. And so now we have our simple or our linear regression function or class that we import from Scikit-Learn. That model actually has a fit method. So this actually does all of the training for you. When we come back to this later on in the quarter, to make it from scratch, we'll actually implement our own method. But for now, our linear regression will do all like the learning right here. And so that basically puts all our data in and fit a slope and a bias to it. And so you can see that coefficient bias by printing it out in the next section. So we can basically see what the model's coefficient of a y coefficient is, as well, or coefficients are, which are weights, the intercept, which is the bias. And so we can print those out. And so it would be different for all of us. We all have different noise because mixed noise is randomized. But it should be around 414, somewhere around it. You might be a bit higher, a bit lower, but you should have a graph in that area. And so everything models like fit that up pretty well. Again, our goal was 4x plus 14. I have 3x, 3.95x plus 14.6, which is pretty close. We're going to calculate an R2 score. So an R2 score is a metric that is commonly used in like statistics as well as machine learning. It's a kind of it's a little bit similar to, I guess, mean squares in a way, but it's let me see, second formula. No, it's basically higher score closer to 1 means very good predictions. Close to the line. Low scores means not close to the line, or close to like a or something like that. So exactly. So we find our R2 score there. Mine's pretty solid, 0.91. Could be improved, but pretty solid. Of course, like you can't expect to have 100% accuracy. Honestly, it's pretty bad to have like perfect accuracy. So anything like above like for getting problems like around 90, 95 is pretty a good sign. So this is pretty solid. Now that we have our R2 evaluation, we're going to figure out our MSE loss. And so to do that, we need to figure out, we're taking that actually, on our test data. And so we're going to have our model predict target prediction scores for our test data and then figure out an error here. So again, we're passing in our test data, we have the team score into our model. It's making a prediction on those test data. And then we're going to compare that to the actual test data target values. Does that make sense, everyone? Any questions about that? Because I went that pretty fast. Yeah. You mean mean squared? It's similar-ish. It's a bit different because the formula is a bit different. If you want to talk about the formula later, well, I won't go into the formula right now, but it's pretty. It is like a similar kind of squarish thing, but it's like a different exact formula. So the results will be a little bit different, but they both are squared. But yeah. So we're going to take our x data, x test data, make a prediction, and compare it, calculate the error with this function. It takes in the y targets and the y predictions, and then calculate the error. So here we have an error of 3 in the 31, which is we have no idea, right? Yeah.
So that's actually a pretty mentioned, right? We have no idea whether 331 is good or bad, right? It's an arbitrary number. What we can do on our R2 score, is that it is less when it's 1. It's kind of a percentage value. The way to use the mean squared error is two things, right? One is what you're actually training. The model doesn't care, right, whether it's percentage or it's number. So if we see the mean squared error decreasing, that's a good sign. This isn't rather than goes from 10 to 1 or from 1 to -5. As long as it decreases, we're good. But something more.
That's mean square. And so now this section, we're going to put our data back on there. We're actually going to see our line. We're going to plot our line with our prediction. So let's do that. And so as you guys see, our line is plotted with this function right here. Plot. And so by looking at this visually, it looks pretty good. And so we can kind of say the eye test, it looks pretty good. And so that's good to see like from our perspective. And so yeah. And so in this case, we basically use the Scikit-Learn model, or the Scikit-Learn linear regression model, to get to some data points and create like a linear regression output, which is a line in this case that fits our data. Any questions about this example?
Yeah, well, let me do one thing. So I just want to quickly go over at a high level what we've done once more. We start with data, right? Second thing we do, we just visualize data. This is actually very important. Get a sense of what data is. data, visualization. Then you choose a model. You've chosen linear regression. You've chosen that y is equal to w1, x1 plus whatever. You chose a model. Then we train our model as a split function. Data, visualization, model, training. Right? Once we have training, we have our weights. Those are what we don't know. So we have our model ready to go. Once we have a model, we want to test question how well, which is what the evaluation provides. Right? And this is just an evaluation. So again, data, visualization, training the model, evaluating the model. That's a very generic pipeline, and it applies to all sorts of things. That's a good kind of structure to say about this. Yeah.
Cool. So we did one part right there. That was like one input, one output, right? So we were given like an X input, we predicted a Y output. So it's a Y equals to P. So now focus on more complex example where we have multiple inputs determining one output. So we're going to go through this imports a data set about diabetes in people and like different factors that cause diabetes. And so this function right here from data sets allows us to load that data set in. So we're going to do that. Again, we're going to split into training and testing data. So we're going to separate out what we train on and what we test on. Then, again, we compare our data, we split it into parts, then we're going to fit our data again. And so we're going to train our model to get data points. And so, you all haven't seen the data set yet, I haven't shown it to you. But there's a pretty big distinction in how the dimensions of this look. And so we'll see it right here, actually. Is that now model.weight is actually, I'm pretty sure, 10 weights now. And so these are basically 10 different features collected by doctors about what how things impact diabetes. Basically, 10 features are being given. So we're trying to figure out if like a prediction about something. And so this is a 10 inputs to one output, basically. And so that's an input. And so now we have 10 weights that were determined by our model that were trained on. They range from really negative to really positive, everywhere in between, like 57 as well. Okay. Yeah. And so with that in mind, we're going to again take the R2 store. So we're going to given our testing data set, we're going to figure out how well our R2 score does. You can see it's pretty bad, right? 0.53 is like really low. It's like way worse than 0.91. And so there's a couple reasons for this. One is that not all data is linear. One of the fiction of linear regression is that it's linear model at the end of the day. And so not all data is linear. And so when you have 10 features, they're more or less and less likely to all line up linearly in a good plane. And so that's what that is. And so if we can figure out mean square as well, it looks pretty big, you can't tell. And so an extension of this that I propose to y'all, if you have time and want to look into this, is looking at only one of the 10 variables from this data set. So exactly only one data set, one data point as an input, and then plot the regression to see why the data set might not be the best. Because my guess is actually that one of the data points is not linear at all with the actual output. So usually our model to be linear, right? Because of linear regression, but that could be quadratic, it could be exponential, it could be any of those things. So more than likely, this data set is not linear in fashion, and we can see that by plotting, comparing the output to each feature individually. And so if you have time, if you want to expose on your own, I definitely recommend it. But with that,
let's go to the last slide. Yeah. So real quick, sorry for the rush. I'm trying to clean up, so just kind of wrap it up real quick. But so yeah, linear regression. Sure. So linear regression is the building block of it all. Okay, literally from this simple model, neural networks. We're going to be using this every single step of the way. We're going to be covering a little more detail next time as well. But you should have a really good sense of what linear regression means. right? I can't even stress how important this is. It's kind of the most important concept in all machine learning, right? Next slide. The next thing we're going to do, we're going to take this linear model, modify it a little bit, and get what we call logistic regression. And this is also very, very important, right? Again, very, very fundamental to machine learning. And we're going to be using to classify objects. It's something a cat, it's something a dog. There's all the classic problems we talked about. We're going to do that in more format, right? So that's also an important concept to talk about. And yes, thank you so much. That is our workshop today. Please try to feedback from if there's a little more exercise. We tried recording for the first time, which was fun.
Yeah, thanks for handling all the things today. We'll be back there, like in CS76 next week, most likely. So come there probably. And we'll have more math about this too, so it'll be a bit more interesting. It'll be more math as well, things like that. So yeah. Thanks all for coming. Yeah.
See ya.
Yeah.
Let's end the recording. 1 second.